This is section 12.2, ANOVA, the analysis of variance. Analysis of variance is used to test whether three or more population means are the same. And in this case, I'm using as an illustration the exercise shown on page 386. It reads, Joyce Coleman manages a regional financial center. She wishes to compare the productivity as measured by the number of customers served among 3 employees. 4 days are randomly selected and the number of customers served by each employee is recorded. And the results are the ones shown here. So the 3 employees are Wolf, White, and Carosa. And for Wolf, these are the 4 employees served. The customers served. For White, these are the number of customers served. And for Carosa, these are the number of customers served. So we're going to test whether the average of each of these employees is significantly different. And first I'm going to do this problem manually so you can understand the numbers that are obtained when you do this in Excel. First of all, I need to calculate the average mean of all the observations of all the numbers. So that's why I place them here in a single column. I rearrange the data this way. Wolf would be these numbers up to 50, 56, White from this to this, and Carosa from 47 to 48, the same as the table here. And I'm going to calculate the average first of all the numbers. So I write equal average B14 through B25. That is 58. 58 is what is called grand mean in your textbook, or overall mean. And so it is 58, and I just going to copy here down, repeat just the number, and that allows me to calculate what is called total variation. Total variation is defined as the difference between the observations, each observation, and the grand mean. So in this case is, for example, for the first row, for the first observation, it'll be B14. Something is, I'm just going to change it to basic colors, it says here, equals B14 minus C14, close parentheses, and then square the difference and hit enter. So if you notice 58 minus 55 or vice versa is 3, square is 9. Then I'm just going to copy this to the rest of the cells. So I calculated the difference between each one of these numbers and theirs, then square them. And the summation of all these numbers is equal to what is called the sum squared. So let me just type here sum squared. And this is called the total variation, sum squared. So it's just the sum of the cells between D14 and D25. Okay? Sum squared. Remember that. Now we can also calculate the mean, the individual mean of each individual. For Wolf, one mean; for White, another mean; for Carosa, another mean. For example, here for Mr. or Miss Wolf, the average is equal average of the cells C14, B14, sorry, through B17. Okay, so that'll be the person called Wolf. I'm just going to copy, obtain for Mr. White or Miss White, and also for Carosa. So these are the 3 means, and I can just obtain the numbers here and copy. Notice I'm just copying the numbers, the same numbers for the 4 observations in each person. And now I calculate the difference between the grand mean and the individual mean, between the overall mean and each mean of the employees, and square it. So that is equal to the difference between E14, that is the individual mean, and C14. Okay. But actually, I'm sorry, I'm just going to do equal E14, that's what I meant to do, minus C14. See the difference, and square, so I'm going to have to go back again. Um, and then square. All right, finally got it done. 56 minus 58, 2 square 4. And if I copy this down, then I get all the differences. For example, 48 minus 58 is 10, square is 100. And of course they repeat because the differences are the same for each individual, except that are repeated 4 times. When I add this up, when I add all these numbers up, I get the sum square of between group differences. It's called between groups. It's the variance, is the dispersion between groups. And so here type equals sum F14 through F25. Okay, so that is my variation between groups. Now the within variation is the variation between each individual and its own mean. So in this case, for example, for the first employee, it'll be for Wolf B14 minus the corresponding average of the group, and that'll be E14. And square that. So that is the first difference, of course, is 1 because 55 minus 56 is 1. Square that is 1. And then copy this down to the remaining cells and obtain the difference between each individual and its own corresponding average. Okay, and that is called within variation. And when I add that column up, then I get the within group variation. So I'm just going to sum here G14 through G25, and that gives me 90. Okay, this is called the sum square. Okay, you can align this well, and if you notice, the between group variation plus the within group variation is equal to total variation. Okay, which is something very important and important to remember. That means that if we have total variation and we have between variation, then we don't need to know this one because 1082 minus 992 give us 90. Because of the basic information that total variation equal between group variation plus within group variation. And so that was SS, or sum of squares. Now here I'm going to type what's called degrees of freedom. The degrees of freedom for the variation between groups, this is the variation, what is called in your textbook, variation between treatments. And the treatments are just the number of people in this case, Wolf, White, and Carosa. These are 3 people, so the degrees of freedom is 3 minus 1. And if you read in your textbook, it is K minus 1, where K is the number of treatments. In this case, case is the number of groups. So it'll be 3 minus 1. The variation within groups the variation within groups is defined, the degrees of freedom for the variation within groups is defined as, or is equal to, n minus k, where n is the number of numbers that we have. So we have 4 numbers per person times 3 is 12. 12 minus 3 people is 9. So this is the degrees of freedom for within groups. And then the total degrees of freedom is just the addition of 9 and 2, and that is 11. And actually, the degrees of freedom for the total variation is n minus 1. In this case, 12 minus 1. Now, from here, we can calculate what is called MS, which is mean square. And mean square of the treatments, or MST, is equal to the sum of squares, which is D31, and just divided by the degrees of freedom, E31. Okay, so that is the what is called mean square of the treatments, or MST, in your textbook. And that's for 96. If I just copy this down, I'll get the MSE is called. It's not the MS, the mean square that correspond to within groups. It's called MSE, this number here, 10. MSE stands for mean squared errors, okay? And where does that come from? What does this mean? Well, we are basically calculating variances. If you recall, the way we calculate the variance of a sample from chapter 3, that is equal to the summation of each number, the difference between each number and its corresponding mean, squared, divided by n minus 1. Well, the numerator here is just what we called in our table SS, or sum of squares. And n minus 1 here is what we call degrees of freedom. So when we take every SS and we divide it by the corresponding degrees of freedom, what we're doing is calculating the corresponding variance. All right, so now we can calculate, and if you recall from the section 1, we can calculate a F statistics. And F statistic is a ratio of two variances. In this case, is the variance called MST divided by the variance called MSE. If you divide 496 by 10, you get 49.6. And that was relatively easy. And that value is going to be compared to the critical value of F. If we use a 5% significance level, in this case, we need to look in the table for the F value that corresponds to 2 degrees of freedom on the numerator and 9 degrees of freedom in the denominator. Remember, we divided 496 by 10. So let's look at that. And I have the appendix B here, and this contains all the relevant tables in the book. And until I'm going to stop where I find my F distribution right here for alpha 0.05. And remember, 2 degrees of freedom here and 9 degrees of freedom on the denominator. The intersection of the two gives me 426. So that is the critical value, 426. And obviously, the F test statistic is much greater or larger than the critical value of 426. So therefore, we reject the null hypothesis. And the null hypothesis is that all the all the means of the population all the population means are equal. And the alternative is, well, the means are different or not equal. So if we reject the null hypothesis, that means that the means are different. Okay, because remember, the null hypothesis says that all these 3 means are equal. Okay, so that is the finding, so we reject the null hypothesis. Now in Excel, you can go to data, and this is the easy part. You can go to data and select ANOVA single factor. Click OK, and then input the range and just block all the information, the numbers, the names and the numbers, and then make sure you click the check labels in the first row. Alpha is specified at 0.05, and on the output range, I want to put it here on top, my result, and now I just click OK, and this is the result. These are the results. And if you notice, let me lower this a little bit. If you notice, the results are the same. Source of variation between groups and within groups, 992 and 90. Total 1082. Degrees of freedom, 2 and 9. K minus 1, N minus K. Degrees of freedom here, N minus 1. MS stands for mean square, and this would be 496 is mean square for the between groups, or MST, mean square of the treatments, and the 10 is the MSE, mean square of the errors, or mean square of the within group variation. And the test statistic, this call in this case is F value, is the ratio of 496 to 10, and that is 49.6, and the critical value is 426. All the values are exactly the same. And notice, in addition, we have the p-value, which is 1.38 with 5 zeros to the left. In other words, the value is 0.0000138, which is a lot lower than 0.05. In fact, it is much lower also than 0.01. So regardless of the significance level that we select, whether it is 5% or 1%, we reject the null hypothesis.